So the topic outline is the following: the introduction of reinforced concrete columns, the definition of tied columns, so as with the spiral columns, composite columns, short columns, long columns, and of course the eccentrically loaded columns. This picture is an example of a tied columns. This one is an example of a spiral column, and the bottom picture is an example of a composite columns. For the introduction, columns are structural elements that support axial loads from the roof and floors. They are usually oriented vertically in a building, and a typical cross-section is rectangular or circular. The main vertical load-carrying members in buildings are called columns. The axial loads on a column are usually compressive. As such, columns are often referred to as compression members. The ACI code defines a column as a member used primarily to support axial compressive loads and with a height at least 3 times its least lateral dimension. The code definition for columns will be extended to include members subjected to combined axial compression and bending moment. In other words, eccentrically applied compressive loads, because for all practical purposes, no column is truly axially loaded. Three basic types of reinforced concrete columns. The first type of RC column is the tied columns. Tied columns are reinforced with longitudinal bars enclosed by horizontal or lateral ties placed at specified spacings, generally square, rectangular, or circular in shape. The next type is the spiral columns, are reinforced with longitudinal bars enclosed by a continuous, rather closely spaced steel spiral. The spiral is made up of either wire or bar and is formed in the shape of a helix. The third type of reinforced concrete column is the so-called composite column. This type of column encompasses compression members reinforced longitudinally with structural steel shapes, pipes, or tubes, with or without longitudinal bars. Code requirements for composite compression members are found in section 10.13. So this one is an example of a tied column which is reinforced, of course, by a longitudinal bars, and it is laterally reinforced with a lateral tie or a confinement hook. And this picture is an example of a spiral columns which is reinforced by longitudinal bars and laterally reinforced with a continuous spiral. And this diagram is an example of a composite column which the main reinforcing element is a structural steel member, for example, an eye flange or a tube or any other structural steel element. So there are two types of general classification of columns, and these type of classification are as follows. The first classification is the so-called short columns. So if columns fail due to initial material failure or crushing of concrete with buckling of steel bars or yielding, it is classified as short column. The load it can support is controlled by the dimensions of the cross sections and the strength of the material of which it is constructed. If the height of the column is less than 3 times its lateral dimension, it may be considered as short compression blocks or pedestal. Pedestals may be designed with unreinforced or plain concrete with maximum design compressive stress equal to phi 0.85 Fc prime, where phi is equals to 0.65 according to NSCP 2010, and which is also adapted by NSCP 2015, or the current code. If the compressive strength is greater than this value, the pedestal will have to be designed as a reinforced concrete short column. The another classification of column is the so-called long columns. Long columns are more slender, thus fails by buckling of the member. Bending deformations increase with secondary moments and P delta effect. So in this diagram, um, a column is subjected to bending deformations and P delta effect. So it is classified as a long column. The P delta moment. When a column is subjected to primary moments M, such as those caused by applied loads or joint rotation, the axis of the member deflects laterally. This deflection causes additional moment applied to the column, which is equal to the column load times the lateral deflection. This moment is called secondary moment or P delta moment. If the secondary moment becomes too large, the column is said to be long column, and it is necessary to design its section for the sum of both primary and secondary moments. However, the code permits that columns be designed as short columns if the secondary or P delta effect does not reduce their strength by more than 5%. So the ultimate strength design of a reinforced concrete column. Design principle. So as discussed previously, the vertical main member of a structural frame is called columns. So this member, which is pointed by a red arrow, is what we call the columns. So basically, columns supported the loads above it, or the loads above the floor, and any other superimposed live loads, and any other type of compressive loads. So in designing or in considering a structural frame, so this one is an example of a frame. So in designing, we will consider the most critical column. So the loads which will be carried by that most critical column, we will consider a tributary area. So a tributary area is one half of the length of the other and one half the length of the other side. So for the long side, the tributary length of the long side is just the one half of L1 and one half of L2. Thus, our long side L is equal to L1 plus L2 over 2. And for the short side is also one half of S1 and one half of S2. Thus, S is equals to S1 plus S2 all over 2. So, section. So, if this is our column, so the tributary area, or the loads under that tributary area is this diagram. So, our uniformly distributed load is represented by WU, and this is the short side S, and this one is our long side, and this is the column, the girder, and the beam. Another design principle, or another main point that we should always remember, especially in designing a structural member, is that we will consider both section, the longitudinal section and the transverse section, and whichever the greater computed loads from that particular section, so that will become the basis in designing our structural member. The next topic is the nominal axial load capacity. Take note that for a column subjected purely by an axial load, or the loads being induced in that particular column is just purely axial, so the nominal load Pn is given by the formula. Pn is equals to 0.85 Fc prime times the quantity Ag minus Ast plus Fy Ast, where Ag is equals to the gross concrete area, which is the B times T. Ast is equal to the area of the steel reinforcement. Fc prime is the concrete compressive strength. Fy is equal to the steel yield strength. To counter the effect of possible eccentricities, the nominal strength Pn is multiplied by 0.80 for tied columns and 0.85 for spiral columns. Thus, in when considering the to counter the effect, so this formula will become 0.80 if we will consider that column as tied. So Pn will become 0.80 times 0.85 times Fc prime times the quantity Ag minus Ast plus Fy Ast. So as with the spiral column, so just put the value of the counter effect before 0.85 Fc prime. So the ultimate axial strength, or the phi Pn, is equal to phi times 0.80 if tied column, or 0.85 if spiral column, times the quantity of 0.85 Fc prime times the quantity Ag minus Ast plus Fy Ast. Take note that phi is equals to 0.65 for tied column and 0.75 for spiral columns. So just substitute this value with this phi in the general formula. So Eg is also the gross concrete area for the B times T. Ast is equal to the area of the steel reinforcement. Fc prime is the concrete compressive strength. Fy is equal to the steel yield strength. So another design principles notes in the design. Limits of reinforcement for tied columns, according to section 410.10. AST shall not be less than 0.01 Ag and AST shall not be more than 0.08 of Ag. So the area of our steel reinforcement must be in the range of 1% of Ag to 8% of Ag. The minimum number of longitudinal bars are as follows: 4 bars, or minimum of 4 bars within rectangular or circular ties for tied column, and 3 bars for or within for triangular ties. The sizes and spacing of main bars and ties. So according to section 425.2.3 of NSCB 2015, for longitudinal reinforcement in columns, pedestals, struts, and boundary elements in walls, clear spacing between bars shall be at least the greatest of the three. So A, 40 mm, B, 1.5 dB, where dB is the longitudinal bar diameter, and C, 4/3 of the diameter of the aggregate. So whichever is the greatest, so that value will prevail. So a typical example, or a typical diagram for a tied column is presented in this diagram. So these four are the vertical bars, or the main longitudinal bars, and these green color are the closed ties, or the lateral ties. So the sizes and spacing of main bars and ties. Use 10 mm diameter ties for 32 mm diameter bars or smaller, and at least 12 mm diameter in size for 36 mm diameter 42 mm diameter and 58 mm diameter and bundled longitudinal bars. So take note that for 32 mm diameter bars or longitudinal bars and smaller, we are obliged to use 10 mm diameter as the size for our lateral ties. And for above 32 mm diameter longitudinal bars, use at least 12 mm diameter. The vertical spacing of ties shall be at least the smallest of the three. So it is very clear that the vertical spacing of ties shall be at least the smallest of 16 times dB, or dB is the longitudinal bar diameter, 48 times the tie diameter, and least dimension of the column. Ties shall be arranged such that every corner and the alternate longitudinal bar shall have lateral support provided by the corner of the tie with an included angle of not more than 135 degrees, and no bar shall be farther than 150 mm clear on each side along the tie from such a laterally supported bar. Where longitudinal bars are located around the perimeter of a circle, a complete circular tie is allowed. Limits of reinforcement for spiral columns. So it is also the same with the tied column, that the area of our steel reinforcement must be in the range of 1% of Ag to 8% of Ag, or 0.01 of Ag or 0.08 of Ag. The minimum number of longitudinal bars for a spiral column is 6 longitudinal bars. So it is according to the code. Then the sizes and spacing of spirals. First, spirals shall consist of evenly spaced continuous bar or wire of such size and so assembled to permit handling and placing without distortion from design dimensions. Second, for cast-in-place construction, size of spirals shall not be less than 10 mm diameter. Third, clear spacing between spirals shall not exceed 75 mm nor be less than 25 mm. Then, anchorage of spiral reinforcement shall be provided by 1 1/2 extra turns of spiral bar or wire at each end of a spiral unit. So, this one is an example of a spiral columns. Then take note that the minimum number of longitudinal bars for spiral column is 6, and the lateral reinforcement is a continuous spiral. So it is the pitch or the spacing of the spiral. Then this one is the longitudinal bars, and these diagonal lines are called the spirals or our lateral reinforcement. Sizes and spacing of spirals. A spiral reinforcement shall be spliced, if needed, by any one of the following methods. Lap splices not less than the larger of 300 mm and the length indicated in 1 of 1 through 5 below. For number 1, deformed uncoated bar or wire, splice length is equal to 48 dB. Number 2, plain uncoated bar or wire, 72 dB. Number 3, epoxy coated deformed bar or wire, 72 dB. Number 4, plain uncoated bar or wire with a standard stirrup or tie hook at ends of lapped spiral reinforcement, 48 dB. And number 5, epoxy coated deformed bar or wire with a standard stirrup or tie hook at ends of lapped spiral reinforcement. The hooks shall be embedded within the core confined by the spiral reinforcement. The splice length is equal to 48 dB. Spiral shall extend from top of footing or slab in any story to level of lowest horizontal reinforcement. Where beams or brackets do not frame into all sides of a column, ties shall extend above termination of spiral to bottom of slab, drop panel, or shear cap. In columns with capitals, spirals shall extend to a level at which the diameter or width of capital is two times that of the column. Spirals shall be held firmly in place and true to line. Splices of spiral reinforcement shall be lapped splice of 48 dB but not less than 300 mm or welded. The percentage of spiral steel, or ρS, is computed from the following equation. ρS is equal to the volume of spiral in one loop over the volume of concrete core for a pitch or S. Then ρS is equals to 4ES times TC minus TB over S times DC squared, where AS is equal to the cross-sectional area of a spiral bar, DC is equal to the diameter of the core out to out of the spiral, and dB. The minimum spiral percentage is given by the formula ρS mean is equals to 0.45 times the quantity of AG over AC minus 1 times FC prime over FYH, where AG equals to the gross area, FC prime is equal to the concrete compressive strength, FYH is the specified yield strength of spiral, reinforcement but not more than 415 megapascal. The next topic is the economical column design. In beams where 60% to 70% of its section is under tension and assumed to be cracked, a section can be made economically by making the tension part smaller in area, as in I or T section. In columns where all the concrete is under compression, savings can be made by using a small percentage of longitudinal percentages since reinforcing bars are quite expensive. These can be accomplished by using larger column size and or higher strength concrete. For composite columns, composite compression members include all such members reinforced longitudinally with structural steel shapes, pipe or tubing with or without longitudinal bars. The strength of a composite member is computed for the same limiting conditions applicable to ordinary reinforced concrete members. Any axial load strength assigned to concrete of a composite member should be transferred to the concrete by members or brackets in direct bearing or on a composite member concrete. All axial load strength not assigned to concrete of a composite member shall be developed by direct connection to the structural steel shape, pipe, or tube. According to section 410.17.2, the strength of a composite member shall be computed for the same limiting conditions applicable to ordinary reinforced concrete members. The ultimate strength design phi Pn is given with the formula phi times 0.80 times the quantity 0.85 Fc prime AC plus FyAST plus FyASS for tied reinforcement. And ultimate strength design for spiral reinforcement is given with the formula phi times 0.85 times the quantity 0.85 Fc prime AC plus FyAST plus FyASS, where phi is equal to 0.75 for composite member with spiral reinforcement and phi is equal to 0.65 for other reinforcement or for tied reinforcement. AST is equal to area of reinforcing steel of strength Fy. ASS is the area of structural steel shape of strength Fy, and the AC is equal to the net. For evaluation of slenderness effects, the radius of gyration of a composite column or composite section should not be greater than the value given by R is equal to the square root of 0.2 ECIG plus ESISX over 0.2 ECAG plus ESASX, where I is x is equal to the moment of inertia of structural steel shape, pipe or tubing about centroidal axis of composite member cross section in terms of mm to the fourth, and ASX is equal to the area of structural steel shape, pipe or tubing in composite section in terms of mm squared. A structural steel encased concrete core as an example of a composite column. It is categorized into two. First, for steel pipe filled with concrete, the T minimum is equal to D square root of Fy over 8 ES. And B, for steel tubing filled with concrete, T1 minimum is equal to B1 square root of Fy over 3Es, and T2 minimum is equal to B2 square root of Fy over 3Es. So this diagram is an example of structural steel-encased concrete core with different type of cross sections. Spiral reinforcement around structural steel core, section 410.17.7. A composite member with spirally reinforced concrete around a structural steel core should conform to the following. First, specified compressive strength of concrete Fc prime shall be not less than 17 megapascals. Design yield strength of structural steel core shall be specified. Minimum yield strength for grade of structural steel used but not exceed 350 megapascals. Spiral reinforcement shall conform to section 410.10.3. Longitudinal bars located within the spiral shall be not less than 0.01 nor more than 0.08 times net area of concrete section. Longitudinal bars located within the spiral may be considered in computing A is X and I is X. So this diagram is an example of spiral reinforcement around structural steel core. So as you can see, it is a type of a composite column, then laterally reinforced with spiral. So this one is the spiral reinforcement, and this one is the concrete core, and the red element is the steel tube with this cross section. Still in the design principles, tied reinforcement around steel core, or section 410.17.8. A composite member with a laterally tied concrete around a structural steel core should conform to the following. The specified compressive strength of concrete Fc prime shall not be less than 17 megapascals. Design yield strength of a structural steel core shall be specified. Minimum yield strength for grade of structural steel used but not to exceed 350 megapascals. Lateral ties shall extend completely around the structural steel core. Lateral ties shall have a diameter not less than 0.02 times the greatest side dimension of a composite member, except that ties shall not be smaller than 10 mm and are not required to be larger than 16 mm. Welded wire fabric or of equivalent area is permitted. Vertical spacing of lateral ties shall not exceed 16 times the longitudinal bar diameters, 48 times the tie bar diameters, or 1/2 times the least dimension of the composite member. Longitudinal bars located within the ties shall be not less than 0.01 nor more than 0.08 times the net area of concrete section. A longitudinal bar shall be located at every corner of a rectangular cross-section, with other longitudinal bars spaced not farther apart than 1/2 the least side dimension of the composite member. And longitudinal bars located within the ties may be considered in computing ASX for strength, but not in computing ISX for evaluation of slenderness effects. For special moment frame members subjected to bending and axial load according to section 421.6, the requirements of this section apply to special moment frame members due to resisting earthquake-induced forces and having a factored axial compressive force Pu exceeding AgFc prime over 10. So the first condition is that the shortest cross-sectional dimension measured on a straight line passing through the geometric centroid shall not be less than 300 mm. And the next condition is the ratio of the shortest cross-sectional dimension to the perpendicular dimension shall not be less than 0.4. So this diagram is an example of a special moment frame member subjected to combined bending and axial load. Still in the design principles, for minimum flexural strength of columns, or in section 421.6.2, the flexural strength of any column proportion to resist Pu exceeding AgFc prime over 10 shall satisfy the following. 1. the flexural strength of the columns shall satisfy the following equation. The equation is the summation of M and C must be greater than or equal to 6 over 5 the summation of M and B, where summation of M and C is equal to the sum of nominal flexural strengths of columns framing into the joint, evaluated at the faces of the joint. Column flexural strength shall be calculated for the factored axial force, consistent with the direction of the lateral forces considered, resulting in the lowest flexural strength, while summation M and B is equal to the sum of the nominal flexural strength of the beams framing into the joint, evaluated at the faces of the joint. In T-beam construction, where the slab is in tension, or moments at the face of the joint, slab reinforcement within an effective slab width shall be assumed to contribute to M and B if the slab reinforcement is developed at a critical stage. For the minimum flexural strength of the column, the longitudinal reinforcement, section 421.6.3, the area of longitudinal reinforcement, AST, shall not be less than 0.01 Ag or more than 0.06 Ag. Then, for the transverse reinforcement, or section 421.6.4, the transverse reinforcement shall be provided over a length LO from each joint face and on both sides of any section where flexural yielding is likely to occur as a result of inelastic lateral displacement of the frame. Length LO shall not be less than the largest of the following. First, the depth of the member at the joint face or at the section where flexural yielding is likely to occur. Second, 1/6 of the clear span of the member. And third, 450 mm. So, the code provides that the length LO shall not be less than the largest of the three. Then, the transverse reinforcement shall be provided by either single or overlapping hoops. Spacing of cross ties or legs of rectilinear hoops, HX, within a cross-section of the member shall not exceed 350 mm on center. The spacing of transverse reinforcement. Transverse reinforcement along the length LO shall be spaced at distance not exceeding the smallest of the three. First, 1/4 of the minimum member dimension. Second, 6 times the diameter of longitudinal reinforcement. And third, by equation Sx is equal to 100 plus 350 minus Hx over 3. Take note that the value of Sx shall not exceed 150 mm and need not be taken less than 100 mm. Hx is equal to maximum horizontal spacing of hoop or cross tie legs on all faces of column. For the area of transverse reinforcement, the transverse reinforcement requirements shall be provided unless a larger amount is required by shear strength. 1. The volumetric ratio of spiral or circular hoop reinforcement, ρ sub s, shall not be less than that indicated by A. Ρ sub s is equal to 0.12 Fc prime over Fyh and shall not be less than B. Ρ sub s is equal to 0.45 quantity Ag over Ac minus 1 times Fc prime over Fyh. And number 2, the total cross-sectional area of rectangular hoop reinforcement shall not be less than that given by A. A is h is equal to 0.3 S B sub C Fc prime over Fyh times the quantity Ag over ACH minus 1, and B, A is h is equal to 0.09 SBC Fc prime over Fyh, where ACH is equal to the cross-sectional area of a structural member measured out to out of transverse reinforcement and in terms of mm squared. A is h is equal to the total cross-sectional area of transverse reinforcement, including cross ties, within spacing S and perpendicular to dimension BC. Fyh is equal to the specified yield strength of transverse reinforcement in terms of megapascals, and BC, the cross-sectional dimension of column core measured center to center of confining reinforcement. S. Spacing of transverse reinforcement measured along the longitudinal axis of the structural member in terms of mm. The next topic is what we call the eccentrically loaded columns. So when a column is subjected with an axial load Pu directly towards the center or the geometric centroid of the cross-section of the column, therefore, the column is subjected to pure axial load. But when Pu is situated with a distance of E, or E is equal to the eccentricity, that's why that column is now subjected to eccentrically loaded columns. So we will design or we will analyze that column eccentrically. For the design requirements, the capacity of columns with eccentricity, we shall remember that number one, as eccentricity increases, the area of concrete decreases. CC, and CS decrease. Tensile stress in bars increases, or T increases. Then the nominal axial load Pn decreases and the nominal moment increases. Number two, at balance condition where E is equals to EB, the extreme tension bars yield, or Fs is equal to Fy. For number three, beyond balance condition, the extreme T force becomes limited. Thus, T is equal to ASFy and Mn decreases. For number four, for very large eccentricities, column behaves like a beam, where C is equals to T and P sub n is equals to 0. For the combined axial and bending, the design principle is that columns will tend to bend under the action of moment, which produces compression in one side of the column and tension on the other side. Possible failures under combined axial and bending loads are shown in the given diagrams. So in this diagram, the column is subjected with an axial load and a bending moment. For the analysis of column strength and their combined axial and bending, so the column may be subjected into possible failures due to the various and kinds of loads being induced into the column. So first possible failure is due to the pure axial loads. So when pure axial load is being induced into the column, large axial load with negligible moment, failure under this condition occur by crushing of concrete with all reinforcing bars in the column having reached their yield stresses and compression. So our ultimate strength axial capacity, or phi Pn, is equal to phi alpha times the quantity of 0.85 Fc prime times the quantity of Ag minus AST plus AST Fy. And our ultimate moment capacity, or phi Mn, is equals to phi Pn times the eccentricity. So when a column experiences a balanced loading condition, so balanced loading condition occurs when the tension steel just reached its yield strain Fy over Es and the concrete is strained to 0.003. If the eccentricity of a column is less than its balanced eccentricity Eb, or where E is less than Eb, the column fails in compression. Thus, compression controls. F as 1 is less than Fy, otherwise tension controls F as 1 is equal to Fy. For balanced condition, Cb is equal to 600D over 600 plus Fy. And take note that T is equal to ES Fy, automatic for extreme tension, under tension, check for Fs. Then, we are obliged to solve for the nominal balance load, nominal balance moment, the ultimate balance axial capacity, and the phi MNB. So in this diagram, so the PB, or the axial load balance, is situated from a distance of E is equal to EB from the geometric centroid of the column section. So as what the definition said, that the concrete is strained to 0.003. Other possible condition that a column may experience is the so-called compression controlled. So compression controlled may occur when large axial load and small movement with the entire cross-section is in compression. That's why failure occurs by crushing of concrete with all bars in compression. So for the compression controlled, we will assume the value of C. So typically, C is greater than CB, and the extreme T or the tensile force is non-yielding. Thus, Fs is less than Fy. So we will use phi is equal to 0.65 if it is a tied column. Therefore, P sub n is greater than phi Pn and M sub n is less than phi Mn. So this diagram describes the compression controlled situation of a column. So there is a axial load Pu situated from a distance of E or eccentricity from the plastic centroid of the column section. The fourth condition is tension control. So tension controlled is just in contrast with compression control. While in compression control, large axial load and small moment, in tension control, large moment, relatively small axial load. So the failure initiated by yielding of tensile bars. So the failure happens in the tensile bars of the column section. So for tension controlled, assume the value for C. Thus C is less than or equal to C5, where C5 is equal to 3D over 8. And the extreme T is beyond yielding. Thus, Fs is equal to Fy. Then use phi is equal to 0.90 for the design. Therefore, P sub n is less than Pnb and M sub n is less than Mnb. So this is a diagram showing and describing the tension control where Pn is situated from a distance of E from the plastic centroid of the column section. This example of tied and spiral column, let us try to solve number 1. A square tied column 450 mm on each side is reinforced with 825 mm bars with Fy is equal to 415 megapascals. Determine the safe service axial life load if the axial dead load on the column is 820 kilonewtons. Use Fc prime is equal to 21 megapascals. So for the solution, our age or the gross area of our column is 450 by 450 is equal to 202,500 mm squared. And the steel reinforcement area is equal to 8 times the quantity of pi over 4 times 25 squared is equal to 3,927 mm squared. So the problem asked is that we are going to solve the safe service axial life load. So in order to solve the problem, so let us solve first the nominal axial capacity of column. So P sub n being the nominal capacity or the nominal axial capacity of the column is equal to 0.80 times the quantity of 0.85 Fc prime times the quantity of Ag minus Ast plus Fy Ast. So we used 0.80 since it is a square tied column. So P sub n is equal to 0.80 times the quantity of 0.85 times 21. So substitute all the values. 21 times the quantity of 202,500 minus 3,927 plus 415 times 3,927. So our nominal axial capacity of column P sub n is equal to 4,139.39 kilonewtons. So in basic learning, so the ultimate axial capacity of column must be greater than or equal to PU, or PU must be less than or equal to phi PN. So our PU, or the ultimate load, so we will consider the factor, the axial loads. So for the dead load, the factor is 1.2, and for the live load is 1.6. So 1.2 P sub D plus 1.6 P sub L is equal to 0.65 times 4139.39. So this 0.65 is the value of phi for the current NSCP code. So phi, it is just the value of phi PN. So 0.65, substitute phi 0.65 times 4139.39. So 1.2 times 820 plus 1.6 P sub L is equal to 0.65 times 4139.39. So the result is P sub L is equal to 1066.63 kilonewtons. So this value is the safe service axial live load of our column. Still in the analysis example, so for number 2, we are going to solve for the analysis of a spiral column. So a round spiral column having a diameter of 450 mm, reinforced with 625 mm bars, having Fy equals 345 megapascals. If the surface axial dead load is 900 kilonewtons, determine the safe axial live load of the column. Use Fc prime equals 34 megapascals. We can consider this problem as an example of analysis, since we are given with the cross-sectional dimension of our spiral column of 450 mm diameter, as well as with the material properties such as Fy, Fc prime, the number of our longitudinal reinforcement, which is 625 mm bars, and of course, we are given with the loads, or our axial load in terms of dead load, which is equal to 900 kilonewtons. So for our solution, first we will solve for the gross area of our column. AG is equal to pi over 4 times 450 squared equals 159,043.13 mm squared. Then our steel reinforcement area, AST, equals 6 times pi over 4 times 25 squared equals 2,945.24 mm squared. Then we will solve for the nominal axial capacity of column, our P sub n. So P sub n is equal to 0.85 times the quantity of 0.85 Fc prime times the quantity of Ag minus AST plus Fy AST. We use the value of 0.85 as the value of our counter effect, since the problem is an example of an analysis. So plugging in all the values, P sub n is equal to 0.85 times the quantity of 0.85 times 34 times 159,043.13 minus 2,945.24 plus 345 times 2,945.24. Then we can solve for our P sub n, which is equal to 4,698.24 kilonewtons. So to solve for our problem, which is the safe axial live load, so we will use the condition that the ultimate load is less than or equal to the ultimate axial capacity, given with a formula P sub U is less than or equal to phi Pn. So with a given 900 kilonewton as dead load, we can use the 1.2 P sub D plus 1.6 P sub L as our load combination based on the NSCP 2015. So plugging in with the formula, so 1.2 PD plus 1.6 PL is equal to 0.75 times 4,698.24. 0.75 is the value of our phi. So so it is 0.75 and not 0.65, since the problem is an example of a spirally reinforced column. So plugging in the values, then we can have 1.2 times 900 plus 1.6 PL equals 0.75 times 4698.24. Then we can solve for our P sub L, or our safe service actual live load, which is equal to 1527.30 kilonewtons. Now, we will come to the design example of tied and spiral column. So first, the design principles when designing a reinforced concrete column. So we will assume the value of steel ratio between 1% to 6% of the gross concrete area, or our AST is equal to 0.01 of Ag to 0.06 of Ag. So I am using the book of Engineer Gilisanya, and he suggests that the ideal value in designing the longitudinal reinforcement or steel reinforcement of a tied column, so use the value of 0.15 Ag to 0.03 of Ag. So for number 1, design a square tied column to carry the following loads. For axial loads, DL is equal to 800 kilonewtons, live load of 650 kilonewtons, then shear parallel to one side, DL is equal to 80 kilonewtons, and LL is equal to 90 kilonewtons. Then, as designer, I will use FC prime of 21 megapascals, then bar diameter of 25 diameter, then F with equivalent Fy of 415 megapascal or high yield strength bars, and 10 diameter ties FYH plus 275 megapascals. Then clear protective covering is 30 then I will use 2.5% ratio as steel reinforcement ratio. So solution, so solve for the ultimate loads, or P sub U. Use the combination of 1.2 DL plus 1.6 live loads, since we are given with axial loads of these two kinds of loads, the dead load and live load. So plugging in with this equation, we can have the ultimate load of PU equals to 2000 kilonewtons. Then from the problem, my steel reinforcement area is equal to 2.5%. So AST is equal to 0.025 of Ag, or 2.5% of the gross area of the column. So ultimate axial capacity of column, the same condition, that P sub U is less than or equal to phi sub n, or that P sub U is less than or equal to phi P sub n. So plugging in, so P sub U is less than or equal to phi P sub n is equal to 0.65, then times 0.80 times the quantity of 0.85 F sub prime times the quantity of Ag minus EST plus Fy EST. So the equation being used is this one, 0.65 times 0.80 times the quantity of 0.85 F sub prime, because it is applicable for axial loads, or purely axial loads. So with the solved axial load, which is equal to 2000 kilonewtons, so plugging in 2000 kilonewtons, so 2000 times 10 to the cube, or can convert kilonewtons to newtons, is equal to 0.65 times 0.80 times the quantity of 0.85 times 21 times Ag minus 0.025 Ag, which is the value of AST, plus 415 times 0.025 of Ag. So Ag is equal to 138,456.69 mm squared. So since the problem is to design a square tiled column, so the area is simply side squared, or S times S. So to solve for the side or the cross sectional dimension of the square tiled column, so B is equal to the square root of the gross area, AG. Then B equals the square root of 138,456.69 mm squared. Then B equals 372.10 mm. Or shall I say, the cross-sectional dimension of B equals 375 mm, with the gross area, AG, equals to 375 squared, or 375 times 375 is equal to 140,625 mm squared. Then, after solving the gross area and the size of the square tiled column, so let's proceed with solving for the steel reinforcement area. Since I am given with the 25 mm diameter, so I am now to solve for the number of longitudinal reinforcement of 25 mm diameter that will be used in the 375 by 375 tied column section. So AST is equal to 0.025, or 2.5% of AG is equal to 0.025 times 375 squared is equals to 3,515.63 mm squared. So that is the value of the steel reinforcement area. Then to solve for the number of longitudinal bars of 25 mm diameter, so N is equals to AST over AB. Then AB is the area of one longitudinal bar of 25 mm diameter. So N equals 3,515.63 over pi over 4 times 25 squared is equal to 7.2 pieces, or shall I say, use 8 bars longitudinal bars. So 8 pieces of longitudinal bars for 375 by 375 column tie section. Then for the lateral ties, so we will solve for the effective depth. So the effective depth is just can be derived based in this formula. So D is equal to B minus 30 minus 10 minus 25 over 2. So 30 is the protective covering that I will use. So 30 is the distance from the extreme concrete fiber of the concrete section, or of the column section, to the outer part of the lateral tie, minus the diameter of 10 mm diameter for my lateral tie, minus half of the longitudinal bar of 25, which is 25 over 2. So the effective depth of D is equal to 322.5 mm. Then NU is equal to PU, which is equal to 2000 kilonewtons. So we have already solved for our ultimate load of 2000 kilonewtons. Then since we are given also with the shear loads parallel to one side, so the factored shear V sub U is equal to 1.2 V sub D plus 1.6 V sub L. The same load combination based on the 2015 NSCP if we are given with dead load and live load, but in terms of shear. So V sub U is equal to 1.2 times 80 plus 1.6 times 90 is equal to 240 kilonewtons. Then the AV, or the area of the cross ties along the column cross-sectional column dimension. So A sub V is equal to 2 times pi over 4 times 10 squared is equal to 157.08 mm squared. So this AV is derived from the area of this one leg of the lateral tie and another leg of the lateral tie. So combining the two legs, so that will become 2 times pi over 4 times 10 squared equals to 157.08 mm squared. For further knowledge regarding the shear reinforcement and principle regarding the shear, you can have it from the topic of beams, especially in the analysis and design of beams from the previous chapters. Okay, so continuation with the design example for our tied column. Since we had already solved for our NU, which is also equal to our factored axial load, PU, was 2000 kilonewtons, then the next step is to solve for the shear strength provided by the concrete, since we are given in the design problem with the shear loads parallel to one side. So according to the NSCP 2015, section 422.5.6.1, that for non-pre-stressed members with axial compression, V sub C, or the shear strength provided by concrete, shall be calculated by the formula V sub C is equal to 0.17 times the quantity of 1 plus NU over 14 Ag times the lambda times square root of Fc prime BWD. So that's why we use that formula in our solution. So plugging in all the necessary values, so we can solve V sub C, which is equal to 189.925 kilonewtons. Then take note that our 2000 kilonewtons, we converted it into newtons, so we can have the consistency of our units. So take note that if our factored shear VU is greater than the phi VC, so therefore transverse reinforcement is necessary. So basing with the computed values, so our VU is 240 kilonewtons. So we can say that 240 kilonewtons is greater than phi VC. So we need transverse reinforcement. Then the next step is to solve for the ultimate shear strength, or the phi Vn, or our shear strength, ultimate shear strength. Then the condition is that phi Vn must be greater than or equal to Vu. Then our nominal shear is equal to V sub C plus Vs. So plugging in with the condition or with the formula, so 0.75 times V sub C plus V sub S is equal to 240. So 0.75 is being used as the strength reduction factor, or phi, because we are solving for the shear. So this Vc plus Vs is derived from the nominal shear Vn from here. So plugging the value of Vn, so we can have Vc plus Vs is equal to 240. Then 0.75 times the quantity of 189.925 plus Vs is equal to 240. Then we can solve for Vs, or our shear strength provided by steel ties. So Vs is equal to 130.08 kilonewtons. And take note that this shear strength provided by steel ties must be less than the shear strength provided by steel ties maximum, or V is max. So we can consider our design as okay or acceptable. So V is max is given with the formula 0.66 square root of Fc prime BWD is equal to 0.66 square root of 21 times 375 times 322.5. Then V is max is equal to 365.78 kilonewtons. So after solving the shear strength provided by steel, we can solve for the spacing of our lateral ties, or the steel ties, or transverse reinforcement. So we are given with a formula: spacing is equal to AV FYHD over VS. Then plug in all the values. 157.08 times 275 times 322.5 over 130.08 times 10 cube. We converted the value of our VS to newtons, so we can have the consistency of our units. Then we can solve for our spacing of 107.16 mm, or say 107 mm. And take note that If the spacing is less than 25 mm plus dt, we need to increase the value of AV by either using a bigger bar size or adding more area. Since our spacing S is equal to 107 mm and it is greater than 25 mm plus dt equal to 35 mm, so the design of our spacing for the transverse reinforcement is okay and safe. So after solving for the spacing of our transverse reinforcement, so we need to consider the maximum spacing of our shear reinforcement. So we can finally say that our design is safe and acceptable. So according to the ACI 318M-14, Table 9.7.6.2.2, the maximum spacing of shear reinforcement. So if Vs is less than or equal to 0.33 square root of Fc prime BWT, so the maximum spacing in terms of mm for non-pre-stressed beam or non-pre-stressed structural member shall be the lesser value of d over 2 and 600, and for the pre-stressed beam or structural member, it should be the lesser of 3h over 4 and 600. And if V sub s is greater than 0.33 square root of F sub prime BWD, so the maximum spacing S shall be the lesser of D over 4 and 300 for non-pre-stressed structural member and 3h over 8 and 300 for pre-stressed structural member. So we had already computed for our Vs, which is equal to 130.08 kilonewtons. So we need to solve for the limiting condition. So 0.33 square root of f zero prime bwd is equal to 0.33 square root of 21 times 375 times 322.5. So it is equal to 182.89 kilonewtons. Since our Vs is 130.08 kilonewton, so it is less than the limiting condition of 0.33 square root of f prime bwd, which is equal to 182.89 kilonewtons. So since Vs is equal to 130.08 kilonewtons, it's less than 182.89 kilonewtons. Therefore, we need to use the spacing maximum 1 given by the ECI 318M-14 that for non-pre-stressed structural member, the maximum spacing is the lesser value of D over 2 and 600. So S max 1 is equal to D over 2. So 322.5 over 2 is equal to 161 mm or 300 mm. So we use 161 mm as the maximum spacing for our shear reinforcement. Then for the maximum spacing of ties, so we have the three conditions. Then take note that the maximum spacing of ties shall be the at least the least value or the smallest value of the three, 16 dB or 16 times the diameter bar of the longitudinal bar, which is equal to 16 times 25 equals to 400 mm, and B 48 times dt or the diameter of the lateral tie, which is 10, so 48 times 10 is equal to 480. Then C, the least dimension of the column, which is equal to 375. So 375 is the smallest value. So therefore 375 prevails. So for the summary, our column size is 375 mm by 375 mm since it is a square tied column. Then our main bars, we had already solved for the 8, 25 diameter bars, and for our ties or hoops, so we use 10 mm diameter spaced at 107 mm on center. So we use the spacing of 107 mm on center because it is the smallest value that we have solved based on the shear requirement. So the next example is for the design of spiral column. So the problem is design a round spiral column to support an actual dead load of 900 kilonewtons and an actual live load of 1300 kilonewtons. Assume that 3% longitudinal steel is desired, Fc prime is equal to 27.6 megapascal, and Fy is equal to 414 megapascal. Use 25 mm diameter main reinforcement. Determine also the minimum spacing of 10 mm spiral with FYH is equal to 275 megapascals with 30 mm steel covering. So this is a design example because we are going to design and to determine the size of our cross-sectional round spiral column. And we also need to determine the number of our main longitudinal reinforcement as well as the spacing of our spirals. So solution, since we are um, the loads or the actual loads has been solved or are given, so we need to solve for the factored actual load using the combination of 1.2 DL plus 1.6 LL. So plugging in with the equation, so P sub U is equal to 1.2 times 900 plus 1.6 times 1300, then the value of our P sub U is equal to 3160 kilonewtons. Then AST is equal to 0.03 Ag. So take note that based from the book of Engineer Gilisanya, that the ideal percentage of the steel reinforcement ratio or steel reinforcement area must be within the range of 1.5% to 3%. So that's why we use 0.03 of Ag or 3% of Ag as our steel reinforcement ratio per area. So the nominal actual capacity of spiral column P sub n is given with a formula 0.85 times 0.85 Fc prime times the quantity of Ag minus AST plus Fy AST. So the counter effect value is 0.85 since it is a spirally reinforced column. So after plugging in the values, so we can have our nominal actual capacity of spiral column P sub n, which is equal to 0.85 times the quantity of 0.85 times 27.6 times the quantity of Ag minus 0.03 of Ag, which is derived from the value of AST plus 414 times 0.03 of Ag. So that is our equation for the Pn or the solved equation for our nominal axial capacity. Then for the ultimate axial capacity of column, take note that capacity or the design capacity must be greater than or equal to the factored axial load. So P sub U is less than or equal to phi Pn. So we need to solve for the gross AG, gross concrete area of the column. So 3,160 times 10 to the cube, which is the value of our PU. So we just substitute the value of our PU to this condition. So converted the 3,160 kilonewtons to newtons in order to have the consistency of units. So equals 0.75 times 0.85 times the quantity of 0.85 times 27.6 times the quantity of Ag minus 0.03 Ag plus 414 times 0.03 of Ag. So take note that 0.75 is used as the strength reduction factor since we are dealing with design of spirally reinforced column. So we can solve the gross area of our column, which is Ag is equal to 140,915.24 mm squared. So since it is a round spiral column, so the area or the cross-sectional area of the column is just the area of a circle. So A sub G is equal to pi over 4 times D squared. So substituting the value of Ag, which is 140,915.24, equals pi over 4 times d squared, we can solve for the diameter of our round spiral column. So the diameter or the d of our round spiral column is equal to 423.58 mm. Or shall we say, the diameter is equal to 425 mm. So after solving for the cross-sectional dimension of our round spiral column and the gross section area, so the next step is to solve for our steel reinforcement area. Since in the design we are considering the 3% steel reinforcement area or 0.03 of Ag, so just substitute the value of Ag to this equation. Therefore, AST is equal to 0.03 Ag. So AST is equal to 0.03 times pi over 4 times d squared. So substitute the value of d. Therefore, AST is equal to 4,255.88 mm squared. Then the next step is to solve for the number of the 25 mm diameter longitudinal bars. So the number of longitudinal bars is given with the formula N is equal to AST over AB. So take note that AST is the total area of our steel reinforcement area, and AB is the area of one longitudinal reinforcement with diameter of 25 mm diameter. So 4,255.88 over pi over 4 times 25 squared. So therefore, our number of longitudinal bars required for the diameter of 425 mm round spiral column is 8.67 bars, or shall we say we rounded it up, so n is equal to 9 pieces of 25 mm diameter bars. So this is the continuation of the design example for spiral column. So after solving for the steel reinforcement area, so the next step is to solve for the spacing of our spirals or the spacing of our transverse reinforcement or the lateral reinforcements. So the minimum spiral, so the core diameter or d sub c can be derived from the equation the diameter of the cross section of the round spiral column minus 2 times the cover is equal to 425, which is the diameter of the round spiral column, minus 2 times 30 equals 365 mm. So our core diameter d sub c is 365 mm. And the area of the concrete core a sub c is equal to pi over 4 times 365 squared, which is the value of d sub c. So a sub c is equal to 104,634.67 mm squared. For our gross concrete area, A sub g, so pi over 4 of times 425 squared, so gross concrete area is 141,862.54 mm squared. Then the area of our spiral bar, since the longitudinal bar is less than 32 mm, so the minimum reinforcement for the lateral reinforcement or for the transverse or for the spiral is 10 mm diameter based on code. So A sub S is equal to pi over 4 times 10 squared, so equals 78.54 mm squared. Then, basing on code, so the minimum spiral ratio is given with a formula rho sub S is equal to 0.45 times the quantity of Ag over Ac minus 1 times Fc prime over Fyh. So plugging in the values, so rho sub S becomes 0.45 times the quantity of 141,862.54 over 104,634.67 minus 1 times 27.6 over 275. So that's why our minimum spiral ratio rho sub S is equal to 0.01607. Then for our spacing of the spiral, so rho sub S is equal to 4A sub S times the quantity of dc minus db over S times dc squared. So we had already solved for the rho sub S, A sub S, dc, and the dB and the dC. So the remaining unknown here is the spacing. So we can solve for the spacing of our spiral. So plugging in all the solved values from the previous solution, so 0.01607 is equal to 4 times 78.54 times the quantity of 365 minus 10 over S times 365 squared. Therefore, our spacing of spiral is equal to 52.10 mm. And if we based it on code, so the code further says that clear spacing between spirals shall not exceed 75 mm nor be less than 25 mm. So, so it is very clear that the spacing shall be range, or the clear spacing must be within the range of 25 mm to 75 mm. So let's back to the solution. So our computed spacing of the spiral is 52.10 mm, and it should be less than 75 mm, so it's okay. So it is acceptable. Then for the minimum requirement of the spacing, or the clear spacing for the minimum, S sub C is equal to, the computed value is 52.10, and the limiting condition for the minimum spacing is 25 mm. Since 52.10 mm is greater than 25 mm, so the spacing of our spiral reinforcement is okay and acceptable. So in summary, the column size, or D, the diameter of our round spiral column is 425 mm, and our main bars, we need 9 pieces of 25 mm diameter bars as the main reinforcement or longitudinal reinforcement. And for the ties or hoops, or for the, no, it should be the spirals. So the spiral reinforcement should be 10 mm diameter, is spaced at 52 mm on center. So these ties should be spirals, because we are dealing with spiral column, so it's just a clerical error. So let us come with the third classification of a column, or the reinforced column, which is the composite column. So for this problem, I will going to show you the solution for the analysis of a composite column. So for number one, calculate the ultimate axial load capacity of the composite column shown. Assume Fc prime is equal to 21 megapascals and Fy is equal to 250 megapascals for the wide flange section. So properties of the wide flange section of W14 by 211. So the weight is equal to 315 kilogram per meter. The area is 40,000 mm squared. The depth, or the h, is equal to 399 mm, and the Ix is equal to 1,107 times 10 to the 6 mm to the fourth. That is the moment of inertia along x-axis, and the moment of inertia along y-axis, I sub y, is equal to 429 times 10 to the 6 mm to the fourth. So for our solution, so solve for the area of our structural steel shape. So the ASS is equal to 40,000 mm squared. That is given with the properties already. So A sub C is equal to A sub G minus ASS is equal to 480 squared minus 40,000. So 480 squared is derived from the area of a square section, since it is a square composite section. So A sub C is equal to 190,400 mm squared. So the ultimate axial load capacity is given with a formula phi Pn. So phi Pn is equal to 0.65 times 0.80 times the quantity of 0.85 Fc prime AC plus Fy ASS. So we use 0.65 as our strength reduction factor, since this type of column is a composite column. So phi Pn is equal to 0.65 times 0.80 times the quantity of 0.85 times 21 times 190,400 plus 250 times 40,000. So A sub C is the net concrete area. So that's why we subtracted um, ASS, or the area of the structural shape, from the gross area of the column section. So phi PN, or the ultimate axial load capacity, is equal to 6,967.30 kilonewtons. For the second problem, still in the analysis of the composite column, so the problem goes this way. Calculate the maximum factored axial load that a concrete filled pipe shown can resist. Verify also if this section complies with the requirements of the code. Use Fc prime is equal to 27.6 megapascals and Fy is equal to 250 megapascal for the steel pipe. So for the given diagram, we have a composite column section. So a structural steel shaped pipe is being used, and of course a concrete filled structure inside the structural steel shape. So the thickness of the wall of the structural steel pipe is 12 mm, and the diameter out to out the structural steel pipe is equal to 300 mm. So in order to solve for the maximum factored axial load that a concrete field can resist, we need to solve first the minimum thickness as per code. So verify if the section complies with the code. So as per code, thickness minimum is equal to d squared of Fy over 8ts. So plugging in the values, T minimum is equal to 300 times the square root of 250 over 8 times 200,000. 200,000 is the equivalent of ES, or the modulus of elasticity of steel. So T minimum is equal to 3.75 mm. Since the given structural steel shape has already the wall thickness of 12 mm, so compare the T minimum, the computed T minimum, with the properties of the structural steel shape. So 3.75 is less than 12 mm. So the structural steel shape section is complied with the requirements of the code. The next, solve for the area of the concrete. So the area of the concrete can be derived by just simply subtract the diameter of the diameter out to out by 2 times the thickness of the structural steel shaped wall. So 300 minus 2 times 12 mm, that will become 276 squared. So area of the concrete is equal to pi over 4 times 276 squared equals 59,828 mm squared. Then the area of the structural steel shape is, or can be derived by simply um, subtracting the whole area of the section by the area of the concrete. So ASS is equal to pi over 4 times 300 squared, which is the diameter out to out, minus 276 squared, which is the diameter of the concrete inside the steel shape. So ASS is equal to 10,857 mm squared. So to solve for the maximum factored axial load that a concrete field can resist, we need to use the condition or the design principle that the ultimate axial capacity of the column shall be greater than or equal to the factored axial load, or in equation, P sub u must be less than or equal to Pn. So Vpn is equal to 0.65 times 0.80 times the quantity of 0.85 Fc prime AC plus Fy ESS. So we use the Phi 0.65 as the strength reduction factor, since this problem is dealing with composite column section. So Vpn is equal to 0.65 times 0.80 times the quantity of 0.85 times 27.6 times 59,828 plus 250 times 10,857 is equal to 2141.26. That is the value of our VPN. So VPN is equal to P sub U. So plugging in the value of VPN with this equation, so P sub U is equal to 2141.26 kilonewton. So that is the maximum factored axial load that a concrete filled pipe can resist. Alright, so we will solve our last problem for the topic 7, columns. So this problem is under eccentrically loaded column. So for problem number 1, the column in figure 5.32 is reinforced with 10 32 mm bars distributed around the perimeter. Load Pn will be applied with eccentricity E about the strong axis or at x-axis. Material strengths are Fc prime equals 34 megapascals and Fy equals 415 megapascals. The neutral axis C is equal to 360 mm from the extreme concrete in compression. Determine the nominal column load and its eccentricity. Find also the ultimate column strength Pn. Alright, so for this problem, we are tasked to solve for the nominal column load or P sub n, the eccentricity E, and of course the ultimate column strength, which is phi P. So our nominal load phi Pn is situated in this particular manner at a distance E or eccentricity from the centroidal axis of the column section. So eccentricity is the distance from the centroidal axis to the applied column load. So with the given neutral axis C is equal to 360, so 360 is now the basis for the division of the compression part and the tension part of our column section. So within 360 from the extreme concrete compression fiber, from here to 360 mm, that is the part of the compression. Remember, all bars in that part will be subjected to compression, and from 360 to the extreme concrete fiber of the tension part, in that part all bars will be subjected to tensile or tension. Okay, so for solving the problem, first we will identify the material properties or the given properties. So our size of the longitudinal reinforcement is 32 mm. So we can solve for the area of that particular bar. So A sub B is equal to pi over 4 times 32 squared is equal to 804.27 mm squared. And to solve for the beta 1, so we will consider the compressive strength of the concrete, or the Fc prime. Since Fc prime is equal to 34 megapascals, so as the code provides, if Fc prime is greater than 30 megapascals, therefore we use the formula for beta 1 like this. So we cannot use directly beta 1 is equal to 0.85 since the given Fc prime is greater than 30 megapascals. So plugging in the values, so beta 1 is equal to 0.85 minus 0.05 over 7 times the quantity of 34 minus 28 and shall not be less than or equal to 0.65. So we can solve for the beta 1, which is equal to 0.8071, and it is less than 0.65. So our computation for beta 1 is right or okay. Then after computing for the beta 1, we can now solve for A, or the Whitney stress block, or it is the distance covered by the concrete compressive stress. if we base it on the stress diagram. So A is equal to beta 1 times C. So this formula is the same in finding the Whitney stress block in flexural beams. So the formulas that we have used in finding or in analysis and design of the beams can also be applied in this particular problem. So A is equal to beta 1 times C, then substitute the value of beta 1. So A equals 0.8071 times 360, which is equal to 290.60 mm, or that is the distance of the Whitney stress block. So this is our value of A, 290.6 mm. And to solve for the concrete compressive force CC, or this is the resultant force of the stress induced by the concrete. So this one. So CC is equal to 0.85 times FC prime AB. Then substitute all the values. So CC equals 0.85 times 34 times 290.6 times 350. Then CC, or the concrete compressive force, is equal to 2939.42 kilonewtons. So we have already solved the value of CC. Then for the stresses in steel, so basically after dividing the column section into two, basing on the neutral axis with a given neutral axis of 360 mm. So the left part from 360 to 680 mm. So this section experiences tension, while the right section experiences compression. Okay, so let us solve first for the stresses of the steel bars in the tension part. So we will label um, these three bars as row 4, row 3, row 2, and row 1. So row 4 and row 3 belongs to the tension part, and row 2 and row 1 belongs to the compression part of the concrete section. So let us solve first for the FS4, or the farthest steel bars from the concrete compressive or concrete extreme concrete fiber section. So FS4 is equal to 600 times 613 minus 360 over 360, or it is just in the formula, Fs for tension is equal to 600 times the quantity of D minus C all over C, where D is the effective depth from the extreme concrete fiber. So 613 can be derived by subtracting 680 by 67. So our basis for the computation of the effective depth shall be from the extreme concrete fiber. So 680, the whole section length, minus the concrete covering, which is 67. So 680 minus 67 is equal to 613, minus 360 is equivalent to the neutral axis C, all over C, all over the neutral axis. Therefore, our Fs4 is equal to 421.67 MPa, or megapascals, and it is greater than Fy. So therefore, our Fs4 has yield. So use Fs4 equals 415 megapascals. Still in the tension part, we will now solve for the Fs3, or the tensile strength of row 3. So with a basic formula, Fs is equal to 600 times D minus C all over C. So Fs3, or in row 3, is equal to 600 times 431 minus 360. So 431 can be derived by subtracting 680 minus 67 minus 180. Then minus the C, which is equal to 360 all over C, 360. Then we can solve for the Fs3, which is equal to 118.33 megapascal, and it is less than Fy. Therefore, Fs3 is equal to 118.33 megapascals. So after solving for the tension part, now let us come in solving the steel bar stresses in the compression part. So in the compression part, row 2 is subjected also to compression, and as well as the bars in row 1 are also subjected to compression. So let us start by solving the Fs2, or for the row 2. So for compression part, Fs is equal to 600 times C minus D prime all over C. So Fs2 equals 600 times 360, which is C, minus 249, which is D prime. So 249, or D prime, can be derived by adding 67 plus 182, since we are considering row 2. So 182 plus 67 is equal to 249 over 360. Therefore, Fs2 is equal to 185 megapascals, and it is less than Fy. Therefore, Fs2 is equal to 185 megapascals. Then to solve for our Fs1, since these bars are subjected to compression, so Fs1 is equal to 600 times C, which is 360, minus D prime, or the effective depth. So D prime is equal to 67, since we are considering row 1, over 360. So Fs1 is equal to 488.33 megapascal, and it is greater than Fy. Therefore, Fs1 is equal to 415 megapascals. Then to solve for the forces of these bars in each part, in tension part and in compression part, so we will denote T4 and T3 as our tensile forces, while CS2 and CS1 as our compressive um, steel forces. So these two act in the compression section of the column. So basically, in solving for the forces, just use the basic formula of force, or stress is equals to force over area, then cross multiply to solve for the force. So T4, consider row 4. So T4 is equals to the stress of the bars, or Fs4. Fs4 has been already solved, so we will solve for the missing parameter, which is the area. So in row 4, or in T4, there are 3 tensile bars. So therefore, our area is 3AB. So T4 is equal to 415, which is Fs4, times 3 times 804.27, which is the value of our AB. Okay, so for T4, or the tensile force 4, is equal to 1001.32 kilonewtons. Then for tensile force 3, T3, so the area covered by this force is 2 longitudinal bars. Therefore, our area is 2AB. So T3 is equal to Fs3 times 2AB is equal to 118.33 times 2 times 804.27. Therefore, T3 is equal to 190.30 kilonewtons. Then for the compressive forces which act in the compression section, so CS2, so there are two area which covered this particular compressive force, CS2. So therefore, CS2 is equal to Fs2 times 2AB is equal to 185 times 2 times 804.27. Then the value of our compressive force S2, CS2, is equal to 297.60 kilonewtons. And lastly, for our compressive force S1, so the covered area for this particular force is 3 longitudinal areas. So CS1 is equal to FS1 times 3AB equals 415 times 3 times 804.27, which is the value of 1 area of bar. Therefore, CS1 is equal to 1001.32 kilonewtons. After solving for the tensile forces of each section, the tensile, the tension, and the compression section, so we can now solve or find the nominal axial load P sub n. So we have already solved for the point load of each section. So we have already solved for the tensile forces in the tension part and the compressive forces in the compression part, as well as the CC. So by the equation of equilibrium, so summation forces vertical equals to 0, we can now solve for the Pn. So Pn is equal to Cc plus Cs1 plus Cs2 minus 3 T3 minus T4. So, or you just summing up the forces, but consider the sign. So P sub n is equal to 2939.10, or just substitute the values of all these forces. So Pn is equal to 2939.10 plus 1001.3 plus 297.60 minus 190.30 minus 1001.30. Therefore, our nominal axial load of our column P sub n is equal to 3046.40 kilonewtons. Then to solve for the eccentricity, or the distance from the geometric center to the center of the axis of the column section to the nominal load P sub n, so we will also use the equation of equilibrium through moment. So summation moment at O is equal to 0. So P sub n, so the moment arm of P sub n is equal to 273 plus E. So P sub n times the quantity of 273 plus E is equal to, let's start with T3. So negative T3 times the moment arm of 182 plus CS2. So the moment arm of CS2 with respect to point O is the quantity of 182 plus 182, or twice the distance of 182, plus CS1, the moment arm of the CS1 is 3 times the distance of 182, plus the CC, or the concrete compressive force. So we will resolve the uniformly distributed force into a single or a point load CC. So we have already solved CC in the previous solution, which is equal to 2939.42. Then the moment arm of our CC is 613 with respect to O. So 613 minus the distance of the uniformly distributed load, so 290.60 all over 2, since we will resolve this uniformly distributed to a point load or a single load. So plugging in the values of P sub n and all the values of the forces that we have solved already, so 3046.40 times 273 plus E is equal to negative 190.30 times 182 plus 297.60 times 182 plus 182 plus 1001.30 times 3 times 182 plus 2939.10 times 613 minus 290.6 all over 2. Therefore, we can now solve for our eccentricity. E is equals to 382 mm. So that is the eccentricity of our nominal load Pn from the centroidal axis of the column section. Finally, we can solve for the ultimate strength of the column. Let us remember that when Fs, or the tensile stress in the tension part, is greater than Fy but less than 1000 megapascals, therefore it is considered as transition zone, or it is within the transition zone of compression controlled and tension controlled section. So if the column section falls under the transition zone, therefore our phi, or the strength reduction factor, shall be computed based on this given formula. So phi is equal to 0.65 plus 0.25 times Fs minus Fy over 1000 minus Fy. Then, plugging in all the values, so 0.65 plus 0.25 times 421.67. So this value is derived from the tensile stress Fs4 of the tension part. Minus 415 over 1000 minus 415 is equal to 0.6529. So our phi, or the strength reduction factor, is less than 0.65, therefore it is acceptable or okay. Then finally, our ultimate strength VPN is equal to 0.6529 times 3046.40 is equal to 1989 kilonewtons. So 1989 kilonewtons is the value of the ultimate strength of the column. So that ends my report. Thank you for listening, guys. And um, I would like to apologize for some background music na hindi ka aya-aya, gaya ng mga sounds ng iba't ibang klaseng hayop dito sa amin kasi naka-GCQ po kami. So, pasensya na po and God bless as all. Thank you guys.